What's up, geeks, and welcome to the channel. Recursion can be tough to understand, especially for new developers. And simply put, a recursive function is one that calls itself. But how do we know when recursion is the right approach, and how can we ensure it works as expected? Let's explore this with a practical example. Imagine we're in a library with numbered shelves where books are randomly stored and we need to find a specific book. The intuitive solution would be to start with the first shelf and search through its contents. If the book is there, we're done. If it's not, we move to the next shelf and repeat the process. This is the iterative approach. We go through each shelf one by one using a loop. In this approach, we start with the bigger picture that is searching through all the shelves. To implement this, we write a loop to go through all the shelves. And then we add the logic to search for the book on a single shelf. This means we tackled the whole problem first and then focused on the smaller parts. Now, to think about this recursively, we'll need to flip this process. Instead of focusing on all the shelves at once, we start by writing the code to search a single shelf. Once that's done, if the current shelf doesn't have the book we want, the method calls itself with the next shelf number. The recursion continues until we find the book or run out of shelves. You see, recursion is about simulating a loop with a twist. It focuses on solving smaller portions of the problem first and then builds up to solve the larger problem. Our task wasn't just to search one shelf for the book, it was to find it among all the shelves. By first solving the smaller problem, that is, searching one shelf, and then applying that same logic recursively to all the others, we end up solving the whole problem. By approaching the problem this way, we've shifted from thinking iteratively to thinking recursively, focusing on solving one part of the problem and letting recursion handle the repetition. Let's solidify our understanding of recursion with a classic example, calculating the factorial of a number. The factorial of a number n, represented as n factorial, is the product of all integers from 1 to n. For instance, 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120. To solve this problem recursively, we identify the repetitive pattern. The factorial of n can be expressed as n times factorial of n minus 1. This formula encapsulates the repetitive logic needed for recursion and translates into code with the method we see. However, this implementation is incomplete because it will be called indefinitely. Why? Well, let's try to call it together. The first time we invoke it, it will have 5 as argument and will insert a first entry in the call stack of our memory. Next, it will be 4, then 3, then 2, then it will keep going. What's stopping it? Nothing. This will eventually result in a stack overflow exception. To solve this, we need to add what we call a stop condition or abort condition, also known as the base case. This condition will tell our method to stop invoking itself recursively and start generating the result for us. In this example, the base case is, if n equals 1, the method should return 1 as factorial of 1 equals 1. When the recursive calls reach this point, the method stops recursing and starts returning values back up the call stack. Here, 1 is returned, then 2 times 1 equals 1, 3 times 2 equals 6, 4 times 6 equals 24, and finally, 5 times 24 equals 120. This example demonstrates that recursion works by breaking a problem into manageable subproblems, solving them, and combining the results to address the larger problem. Now, let's explore another example, the Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, starting with 0 and 1. For example, the sequence begins as 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Mathematically, the Fibonacci number at position n can be defined as Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. To write this recursively, we need a method that takes an integer n as input, representing the position of the Fibonacci number we want to calculate, and returns the corresponding value. For instance, calling the method with n equals 7 should return 13, as 13 is the 7th number in the sequence. What we see is the basic recursive implementation in Java. But like the factorial example, this method is incomplete because it lacks base cases which are critical to prevent infinite recursion and stack overflow errors. Since the Fibonacci sequence starts with defined values, Fibonacci of 0 is 0 and Fibonacci of 1 is 1, we need 2 base cases. The complete implementation would look like this, and here's how it works. Calling Fibonacci of 5, for example, triggers recursive calls, breaking the problem into smaller parts until the base cases Fibonacci 0 and Fibonacci 1 are reached. These base cases return their respective values, 0 and 1, which are then summed up through the recursive chain to produce the final result. This example highlights the essence of recursion, breaking a problem into smaller manageable parts, ensuring that base cases define where the recursion stops, and combining the results to solve the overall problem. Okay, now that we understand how recursion works and how we can solve problems by breaking them into smaller subproblems, let's take it a step further. While standard recursion works fine for many problems, it can lead to excessive memory usage and slow performance when dealing with deep recursion. This is where tail recursion comes in. Tail recursion is a special form of recursion that has unique advantages. Let's discuss what distinguishes tail recursive methods from regular recursive ones, how to transform a regular recursive method into a tail recursive one, and why we might want to do that. At its core, a method is considered tail recursive when the recursive call is the last action performed before the method returns. This simple distinction has profound implications for memory optimization thanks to a concept called Tail-Call Optimization or TCO. While many compilers and programming languages can leverage TCO to improve efficiency, the JVM currently does not. Nevertheless, understanding tail recursion is essential for writing efficient, scalable recursive methods. To illustrate the difference, let's start with the factorial problem. In our previous example, we implemented the factorial recursively. Let's bring back that implementation. Now, if we wanted to optimize this method to be tail recursive, we need to ensure that the recursive call is the last statement executed. To do this, we introduce an accumulator parameter to hold the intermediate results and make the recursive call the last operation. What you see is the tail recursive version. Notice that in this tail recursive method, the recursive call is the last operation performed. The accumulator keeps track of the intermediate result, and once the base case of n equals 1 is reached, the final result is immediately returned. Next, let's consider the Fibonacci sequence problem. In a non-tail recursive Fibonacci implementation, we would make two recursive calls at the end of the method, and the addition would be the last action we perform. This implementation is simple, but it's inefficient due to the repeated calls for the same values. We can optimize it using tail recursion by keeping track of the two previous values in the sequence. Here's how we can rewrite it as a tail recursive method. In this tail recursive version, we pass along the previous two Fibonacci numbers, a and b, and update them as we go. When n reaches 0 or 1, we return the appropriate value, ensuring that the recursion terminates without further work after the final recursive call. Now, let's take a look at a new example, the sum of numbers. Imagine you need to calculate the sum of numbers from 1 to n. A simple recursive approach might look like this. And to convert it to tail recursion, we need to accumulate the sum as we go. In this tail recursive version, we pass an accumulator that holds the running total. Once n reaches 0, the final accumulated sum is returned. In all of these examples, transforming the recursive methods into tail recursive ones allows us to take advantage of tail-call optimization. This means that the recursive calls can be optimized to avoid using additional stack space, reducing memory consumption, and preventing stack overflow errors in cases of deep recursion. With that said, let's visualize the stack memory of one recursive method we implemented to better understand how tail recursion works and why tail-call optimization can be so important. In the factorial example, when factorial 5 is invoked, the recursive calls are added to the stack sequentially. We cannot start popping from the stack until we reach the recursion's stop condition. When that happens, the values we have will start to get replaced and the stack calls will pop. However, if we try this on the tail recursive method, the first call is that of the factorial method and the second is that of the recursive call. When factorial 4 is called, because no variables are required to be stored in the frame left by the parent call of the same recursive method, and because both of these calls will have the same return value, then the same frame will be used to store the new call details. Now, if we go ahead and compare the stacks corresponding to the recursive methods at their maximum depth, you will see that the space complexity of recursion was reduced from O of n to O of 1 thanks to tail call elimination. By understanding the differences between standard recursion and tail recursion and knowing how to transform one into the other, we can write more efficient and scalable recursive methods that handle large inputs more gracefully. And that's it for this video. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.